All right, good day, everybody. Today I'll look at the last thing I decided to optimize, and that's for a fixed volume cone. What's the maximum elevation, vertical elevation gain? And that's assuming you go from one side of the cone to the exact 180 opposite side. So pictorially, like for this one right here, I've got a couple cones. So here along the base, if you go to the exact opposite, the angle, so you can pop this out. It's just when I join these two ends here, the angle will be, so whatever the midpoint or mid angle of this is, 180. So this wasn't too bad to find, but so this angle is, I call this alpha. So half of alpha just added to pi. And so, you can draw a straight line and have it done pictorially. So if you make the cone like so, then you can see the geodesic. So I want the shortest distance to go across. There's actually two. There'd be one the opposite way, but or reflected way, whatever. Since it's the exact opposite, going the other way. But anyway, so I want, what's the highest, like if you call it the Z direction, what's the most I go in the Z direction? It turns out the taller the cone, you're not going to go as tall. So we've seen some of the cones I have, and we'll see more done. Let's see real quick. Here's my tallest cone. So with the tallest cone, so you actually don't go very high at all. You can't quite see it in the bird's eye view. Maybe you can. But so being too tall is bad, and of course being too short would be bad. I have a real short one here. This cone was made by cutting out pi over 6, 30 degrees to get a real short cone. Then this is very far up in the L direction, but it's such a short cone it doesn't matter, right? The elevation climb won't be as much. So there are two of these. Yeah, there's two. Right, so yeah, there's two. Then there's a line of latitude. Oh, it's on this side. Right, so to go from here to the exact opposite, yeah, it's right there. Lost track. So it's very far that way, but because it's such a short cone, you're not going to go as high as you do on here. So there's a balancing act, and calculus will kind of give us the result of which cone maximizes elevation gain. All right, so I call this cone 6. So we're going to minimize the elevation gain going to the opposite side of the cone. So here's a sample cone. The way I have it, I cut from the positive x-axis and I cut an amount that way. So I call that alpha. And this will be amount beta. We're going from here to the exact opposite. So if this is at alpha, so I just need to go an extra beta over 2. So that's what this point is going to be. Right? So if this is alpha, and this is the origin, positive x-axis, this is at L. Now L will depend on alpha, but I'll suppress that notation for now. So L cosine alpha, L sine alpha will be this point, and then this will be at alpha plus beta over 2. To get to the other side and then close it up, it'll just be exact opposite. So alpha plus beta is 2 pi, so beta over 2 is pi minus alpha over 2. Right? Beta is 2 pi minus alpha. So over 2 would be that. Alpha minus alpha over 2 is alpha over 2. And then cosine of pi plus alpha over 2 is cosine cosine plus sine sine, but that'll be 0. And cosine will be cosine of pi, so there's a negative. And similarly, with this. It'll be sine of alpha over 2 plus pi, which will be sine cosine plus cosine sine. The cosine sine term will survive with a pi. Cosine pi will be a negative, which in hindsight maybe makes sense, because if I look at alpha over 2 and then add pi to that, I'd be right here. Or it's the negative of the point that's at alpha over 2. So different ways to verify it. All right, so anyway, so the slope of that line, change in y over change in x, l's cancel. And then, so I have a sum of sines. So it'll be the sum of the two angles divided by 2, so average, and cosine of the difference, and with the 2 out front. So this numerator will be a 2 sine of the sum, cosine of the difference, and both divided by 2, right? So I should have said the sum divided by 2, the difference divided by 2. And similarly, a sum of cosines is cosine of the sum over 2, cosine of the difference over 2. And cosine's even, so it wouldn't even matter about the order there. So here you can cancel out an L. Then the sum of the sines becomes this, the sum of the cosines becomes this. You can see the cosines cancel, the 2's cancel, so there's the slope. So then you can pick either point. I picked this point, so y minus the y value equals the slope, x minus the x value at this point. So I just want the equation of this line, and then we're going to maximize the vertical. We'll find the L distance that way, and then we'll turn it into a vertical distance. So anyway, if I get y, well, let's see, I'll just multiply by the cosine. So y times cosine, L sine cosine equals sine times x, and sine times the L cosine. Move this x over, and then we'll write the equation of this line in polar form, which could be now a little confusing because I use R for the cone, but I didn't want to redo all that work, so I just mentioned. So now I'm using R for polar. So y is R sine theta, x is R cosine theta. And so I can get the equation of the line in polar form is, some more identities. So let's see. Sine cosine minus cosine sine, that's like the sine of the first, let's see, minus the second, right? Sine of the first minus the second. Yeah, just put it up above here. Sine of alpha minus 3/4 alpha. That's a force. Anyway, not readable, but I said it out loud. So sine of alpha minus 3/4 alpha will be sine cosine minus cosine sine. But alpha minus 3/4 alpha is just sine of 1/4 alpha. So this becomes that, which becomes that. And then when I divide, the same thing will happen. So I'll try and write this one a little neater. This is the sine of theta minus 3/4. Well, I guess that's all I wrote. There's no simplifying that. So it's the sine of the first, cosine of the second, minus cosine first, sine second. So that's exactly what that is. So it could be compacted like so. And then R is the distance. So if we look at our cone, got a couple here, one from the base, but one up a different height. This will just be a constant multiple depending on the fraction of the way down you go. It'll be that multiple of the value I'm going to find here. But anyway, so here it is when it's flat. So the elevation, since it's constant slope, it's just where this L is maximized, and that'll be so exactly midway. So if I know these two angles, the R, just ballpark it, but let's say it's like that. So the angle that's midway between here would be where this is closest to the vertex, or equivalently, if this is closest to the vertex or the origin, I should say. So if this is closest to the origin, then this is farthest away from the end of the circle. And then where that's maximized, when you make the cone, that'll be maximum elevation. This is at alpha. This is at alpha plus beta over 2. So I added beta over 2 to alpha. So half of that is beta over 4. So alpha plus beta over 4 will be the angle. So alpha plus beta over 2 or beta over 4. Now beta is 2 pi minus alpha. So 2 pi minus alpha divided by 4 is pi over 2. And then minus alpha over 4. So it look like that. So L is maximized at that angle. And so the max then is L minus, and then another way to see it, actually, when you look at it this way, the numerator is fixed, so I want to divide by the largest possible value. And well, the largest possible value for sine is 1. And that occurs if the argument is pi over 2. And the argument will be pi over 2 if theta is pi over 2 plus 3/4 alpha. So that's another way to see it. And then what is the maximum value of R? I didn't want to keep using R because I use it for different things. But the max is then L minus that. And then I called it K here for something that comes in a later diagram. Because this is the slant length. And of course what I want to actually maximize is the vertical amount. But it'll occur when the slant length is maximized. So, but just for my diagram purposes, I called this maximum value K. So I want to find the cone, again, to get the maximum elevation gain. But alpha is not the only variable here, because to have a fixed volume, if I change alpha, I'll have to change L, so I have the same volume. So for a fixed V, L also depends on alpha. And there's the formula in terms of alpha. Just as a reminder as to how to get L in terms of alpha, right? So you have a cone, volume, let's say it's fixed, pi over 3 r squared h. So change r or h will force the other to be changed, like so. And then the slant length is related to h and r through this Pythagorean identity. So again, so we saw that identity, we saw this identity. So h L squared minus r squared, but r is L beta over 2 pi. Factor out the L. Volume is pi r squared h over 3, or 3v is pi r squared h. So I can get L in terms of beta, which is the same as getting L in terms of alpha. It's kind of a little more complicated, but that was the way I originally thought about it. I kind of thought of the alpha as the action variable, how much I cut, and then beta is what remains after. Now I want to maximize the elevation gain. We'll have to take that into account. So let's see. Because I don't want to just maximize L. The bigger the R is, the bigger L will be. Right? R could be 100. It'd be a super tiny height, which means I won't have much of an elevation gain. So it's not just maximizing L, but the elevation gain. So by similar triangles, I should probably have started with this one, but you don't have to be at the end. I kind of did it in general first, but then I decided to do it in terms of this amount here. So K is the amount for the elevation gain if you start at the base and then go to the exact opposite side. What will this elevation gain be? The Z part. So we just found the K right here, and then now by similar triangles, the elevation gain, so this vertical amount, which I put right here, over this hypotenuse K, is going to equal the height of the finished cone over L of the finished cone. So I need to know the height of the finished cone. So my elevation gain will be H over L times the K. And well, when we look at the K had a factor of L. So H over L times this K, the L's will cancel. And so I just get H. Oh, yeah, there it is right there. So H times that. And of course, H depends on alpha. So here it is. So actually, I guess I started to show it and then I left it. So back to my work. 2 pi r equals L beta. So beta is 2 pi r divided by L. That's in terms of r. Let's see. L is the square root of r squared, but r squared is 3v over pi h. And r is the square root of that. So put it on top and bottom. And then simplify. Maybe multiply top and bottom by square root of pi h. So there's beta in terms of h, which means I can get h in terms of beta. Well, in this case it means it's nice and solvable. So we'll square both sides, cross multiply, and I get pi h cubed is this, so h is this in terms of beta. Or changing it in terms of alpha, beta is 2 pi minus alpha, so just put a 2 pi minus alpha everywhere. I can have h in terms of alpha. So the elevation gain, h times this, but h depends on alpha, like so. So then the elevation gain, there's the h in terms of alpha, times a 1 minus sine alpha. And it's maximized when the derivative with respect to alpha is 0. So this I farmed out. So here's a plot, or there's the function I want to maximize. Again, depending on where you start, how far down along L. In the end, I did you could do some multiple of that, some fraction of the way down, but we want to go 100% of the way down or 1 of the way down. And so here's a plot. So it's maximized at this value of alpha, so almost 1.35. And then this will be the maximum amount. Found it a few different times, simplified, and then there's the beta. So almost 5 radians. So it's a pretty short cone. So I'll look at some pictures, but so here's 1.35, as I said, is roughly it. And all right, so I'll first do it with alpha equal to 1.35, and I'm going 100% of the way down from the vertex along L. D is just for the window. So now I'm going to put them together. by lifting up. So as I lift up, this is the shape, and there's the elevation gain, as you see. So again, that's the max possible, 2.4922. So if you go from one side to the other, that's your elevation gain. You know, if you're an ant that wants to walk the shortest distance to get to the other side, you don't care about elevation gain. That would be, in this case, centimeters is the units I use. And it's just that percentage if you start part of the way up. So if I start at, say, 70%, it looks a little neater. So now I'm starting 70% of the way. I don't know what the L is a teeny bit larger than 6. It's like 6.0 something. So it's almost the same as the minimizing L problem, but it was a little bit different. So L's a slightly larger than 6. And so 70% of the way, you know, be a little more than 0.42 or 4.2. Anyway, so if I want to go to the other side, there's the straight line distance I'm going to go. I also drew the latitude line, and then I will see the elevation growing as I close the cone. It was quite the feat to be able to do this. Anyway, so there we go. So there's the elevation gain if you start part of the way up and then go along this path to the shortest distance. Right? Right, so that's the geodesic graph. And you can do with other angle cuts, right? So let's see, 1.3. What if I were to do, let's say, do a tall one, say a pi. I should have made it 1.0, but well, we'll just leave it. And so if you cut pi, then you get a much taller cone, but you're not going to get the same amount of elevation gain. This path will be much closer to the latitude the taller you are. It doesn't matter where you start. Let's try all the way down again. All right, it's just this multiple. So it's the one we just saw would have been 70% of the one we're about to see. Not changing the angle. All right, so now I'm starting at the base, going to the other side. So there we go. So there's the elevation base gain if you start at the base and go to the other side. So it's not as much. Right? It was like 2.49, I think, for that other cone. And of course, if you go too short, I'll go really short, like pi over 4, 0. Well, let's see. I'll do 0.52. That's the other one I have graphed. Then your L will be a lot bigger. So this is 30 degrees, or pi over 6 is the cut. Right. So this L is much bigger. So you get closer to the vertex, but your vertex is barely above 2.5. So overall, it didn't have as much elevation gain. Make it a little smaller. And cut that in half, say 0.26. So that would be pi over 8, 22.5 degrees. Right, so you're getting much closer to almost just, why not just go straight over the hill? But that would be a longer distance. And I can't help myself. I'll just cut it in half one more time. 0.13. So R is so big for this cone. H is really small. Right, one more look. at the maximum. Again, that'll be about 1.35 radians. So this cut will maximize my elevation gain. All right. I do have it plotted, the final result. So instead of watching it form, we'll just look at all the final elevation gains for different cuts. So first, if I only cut 0.01, I don't quite have it, but I'll start there anyway. So this is the final elevation gain. So here's the cut theta. I should have called it alpha, but so it's going up, and it should keep going up until I get to 1.35. I'll go slowly here. Elevation gain 2.49222. So that's, I think, the max. It's a real stable max there. So 1.34. I think that was it. So there's the max, roughly. I rounded to 1.35. And then we're going to get taller cones, but the elevation gain is going down. Elevation gain goes up, but then gradually you get so short it goes back down again. So there is that maximum. All right, so that's what we found in this problem. I found it interesting, and it wasn't too bad for the calculus, although I had to resort to numerical methods to get the values. The hardest part was plotting it. It took quite the ingenuity to do that. But I'll put my results in the documents. Anyway, so I hope you enjoyed that look at a cone. Thanks for watching. Check out some other cones that have simpler critical values if you like. Anyway, again, thanks and have a good day.